Hello, in this lecture we are going to do Laplace's equation. In this lecture we are going to do the Laplace's equation in spherical polar coordinates. And this is very important. As such, you'll find too many physical applications having some spherical symmetries. So kindly pay attention to this particular discussion. Okay, so we are going to discuss something more concrete, that is Laplace's equation in spherical polar coordinates. Okay, and this is quite important. Everybody knows that it's quite important. Just give me a minute. Okay. मुझे तो share screen. Okay, so this is Laplace's equation in spherical polar coordinates. And this is quite important. Okay, so understand the fact that if I'm saying that my del square V, and in general you will find this kind of thing whenever, even in quantum mechanics, you'll find Laplace's equation in spherical polar coordinates. Right now we are sticking to electrostatics only. So in spherical polar coordinates, if I have to write my del square V equal to 0, what does it imply? It implies 1 upon r square. I think del by del r. You have this r square, then you have del V upon del r, and then you have 1 upon r square sine theta. And then you have, I think, del by del theta. And then you again have sine theta. And then you have again, I think, del V upon del theta. And then you have again 1 upon r square sine square theta. And then you have del square phi of del square V upon del phi square. So this is how you're going to write your Laplace's equation in 3 dimensions in spherical polar coordinates. So Laplace's equation in spherical polar coordinates precisely in 3 dimensions. We can write my Laplace's equation in this way. The best way to solve these equation, or the only way to solve, like the way to solve these equation, is something called as method of separation of variables. So method of separation of variables. So method of separation of variables. This is the way how we actually solve these kind of partial differential equations. In this way, what we do, we actually let us थोड़ा सा इसको homogenize कर देते हैं. So let us first consider that my V can be written as some function of r, some function of theta, and some function of phi. Okay, so we are going to employ method of separation of variables, in which what we do, we actually consider, if it is symbol को थोड़ा easy कर लेते हैं, we use some simple symbol, otherwise this will be difficult for me to draw. P theta, and इसको कुछ कर देते हैं f of phi. Okay, so let us take some easier sort of notation, otherwise things will become difficult as I go along. So overall understand कि करना क्या होता है. All we do is we take product of individual functions. Like for example, we take one radial function, another function that entirely depends on theta, and one other function that completely depends on phi. So this is method of separation of variables. So for example, what do we do? When we insert all these things inside, what will happen? See, here you have this like derivative with respect to r, so you will have 1 upon r square, and you have this del by del r of, you will have r square, and only one component, that is del r upon del r would be there. All other components will come out. That is because here you have to differentiate with respect to r, so you cannot differentiate with respect to theta and phi. So all of these things will come out. So p theta and f phi will come. Is that clear?
Yes, sir.
Okay. Or plus 1 upon r square sine square theta. What will come out? R will come out, and then I think f5 would also come out, and then you have this del by del theta of, if you simply write sine theta, and then inside you can write del p upon del theta, and similarly you can write I think plus 1 upon r square sine square theta, and I think we can write it as correct. I think I will write it as f. Sorry, we'll write it as r p theta, and then this is del square f upon del phi square equals to 0. Okay. So in method of separation of variables, we assume a solution which is a product of individual, which is a product of functions of like individual functions. So for example, one would be a radial function, another function, other one would be a function of theta, another one would be a function of phi. We multiply all these functions, and we say that our potential can be written in this form. So I have like made it in sort of easy notation. Okay. Now what I would do, I would simply divide it by, so divide this entire expression by, divide this entire expression by, I think r, p, and f. So like you understand, this is f is a function of phi, p is a function of theta, r is a function of r. So what will happen? And also multiply by r square sine square theta. So if I multiply by r square sine square theta, what I will get? I will simply get, I think, sine square theta divided by r as a function of r, and then you have del by del r of r square, and this then you have del capital R upon del r, plus here what you will have, I think here I will have something like I think this cannot be sine square theta, it has to be sine theta, right? So it will be like sine theta, and then you will have divided by, why it is going this way, it will be like p theta, and then you will have d by d theta, and then you have, I think, sine theta and del p upon del theta, and then last you will have plus 1 upon f del square f upon del phi square equal to 0. Is that clear? Now what we do, we actually take one variable or one particular like one particular term there on the right hand side. So one particular term I'm taking on the right hand side. What it will come out as? It will come out as f del square f upon del phi square, and there would be some LHS term. LHS term is sine square theta divided by r, and then there would be del by del r, and then there will be r square, and this is del capital R, like this is how it is, plus sine theta divided by p, and then you have this del by del theta, sine theta, and then you have del p upon del theta. And this is equal to 1 upon f del square f upon del phi square. Okay. Now you see that this is alone a function of phi, and this is alone a function of r and theta. So you can see that here you have function of r and theta. Like all other things are taken constant here. So this is on the right hand side you have functions of r and theta. On the left hand side you have function of phi alone. Is that clear? Because if I am differentiating with respect to phi, I am taking r and theta as a constant. So I have only a function of phi here, and you have function of r and theta alone. So what can be one possible solution? That if at all their sum is 0, it implies they must be equal to some constant. And if it is equal to some constant, let's say anything, then equal and opposite constant should be here. So for example, if I equate it to minus m square, then this entire thing should be plus m square. Is that clear or is that not clear? So method of separation of variables, you can see what I have done. I have used like this as a solution. And then after certain simplification, I have arrived at this. And if I take this on the right hand side, now I know this f is a function of phi alone, and all these, like here you can see on the left hand side, you have function of r and theta, because all other terms are taken as a constant when I'm differentiating, partially differentiating with respect to theta and partially differentiating with respect to r. So understand my point. I'm saying if their sum is 0, then it is only possible if they can be equated to some constant. So let's say I equate it to some m minus m square. And if it is minus m square, then this would be some plus m square. Only in that case, I can have some sort of solutions. Is that clear or not clear?
Yes, sir.
Okay. Or thoda sa we'll have to take the use of thoda sa we'll have to हम exact solutions को नहीं निकाल पाएंगे, but we'll have to take use of something called as Legendre differential equations, the form of Legendre differential equation. We have to accept the fact कहीं कहीं पर. So for example, I will write my 1 upon f del square phi upon del phi square as minus of some m square. You can say no, because this उधर की तरफ जाएगा तो minus हो जाएगा. So minus of m square. So f as a function of phi, f as a function of phi, I can write it as uh, so for example, if you write e की power iota m phi, and you can take plus minus also here. So this will be your f as a function of phi. Is that clear? You just equated this term, so इधर की तरफ लिखा होगा तो negative हो जाएगा. You equated this term to m square. Okay, you equated this term to m square. Is that clear? Or since phi goes from 0 to 2 pi in spherical polar coordinates, so m and m belongs to z. So m belongs to z. Is that clear? बढ़े आके यहाँ तक कोई प्रॉब्लम तो नहीं ना? Now next what we'll do, since we know that we have arrived at f high, we'll do something. What we'll do something is, okay, what we'll do, we'll simply take this radial term here. What is my radial term? My radial term is 1 upon r, and then you have del by del r of I think r square. इसको याद नहीं करना, बस इसके qualitative solutions पे ध्यान देना. Del by del r equals to I think minus 1 upon p. अच्छा एक sin theta भी था, right? One sin theta was also there ना. इस sin square theta को divide कर दो. So what will come out as p sin theta, because here it was sin theta ना. On the numerator I had a sin theta. If I divide by sin square theta, I will have a sin theta, and then you have del by del theta, and then you have again sin theta, and again you have del p upon del theta, and then plus
m square.
Negative is plus नहीं आएगा, negative आएगा. Sorry. Minus what was that 1 upon f ना, तो 1 upon f क्या होगा? अच्छा एक sin square theta तो आएगा for sure. एक sin square theta will anyway come out. Okay. Or what you can see about del square f upon del phi square. So if I want to write del square f upon del phi square, so del square f upon del phi square ऐसा लिख सकता हूँ क्या? देखेंगे. So f was equals to what? A e की power plus minus iota phi, और simply write a e की power iota m phi. इसको दो बार डिफरेंशिएट करेंगे तो कितना आएगा? Minus m square f, यही आएगा. देखो अगर मैं कह रहा हूँ a e की पावर, अगर m belongs to z कर दो तो प्लस माइनस लगाने की जरूरत नहीं. Just write m belongs to z, so it will be a e की पावर iota m phi. Now if you write this as a solution, now what I can write, I can write that my del square f upon del phi square will be m square f, and if I write 1 upon f del square phi upon del phi square, it will be minus m square. So this will be plus here, and this will be m square. Is that clear?
Yes.
Okay. Or I think this is quite clear. Is that clear to you? So होता क्या है? For example, यहाँ तक clear हो गया? Now you see that this is a standard approach in central forces that I'm going to do just right now. But overall understand कि जो left hand side, the left hand side is completely a function of r alone. So I'll write here जिससे तुम्हें समझ में आ जाए. The left hand side is completely a function of r alone. This is a function of r alone, and right hand side is a completely, you can see, as a function of theta alone. This is completely a function of okay. Is that clear? So again, I can write that my entire like you can say that my entire side on either side I can write it as constant, and we take this like for if you solve all these differential equation in greater detail, you will find that usually this constant is taken to be as L into L plus. the constant is taken to be L into L plus 1. I mean, thoda sa isme yaad karna padega. I cannot help it. Otherwise, it will be very difficult. So what I can say that I have equated this entire stuff to L into L plus 1. If it is L into L plus 1, this will become minus L into L plus 1. That is not an issue. But overall, I have written this entire term as L into L plus 1. We'll see why we are doing it when we'll solve this thing in greater detail. We'll see that this will become a Cauchy-Euler equation. But overall, understand what I have done. Since this is a function of theta alone, this is a function of r alone, we can equate them, the individual things, to a constant and let that constant be equals to L into L plus 1. Is that clear to you? So if I write this particular thing as a constant, for example, if I want to find the theta solution at first, so theta, ये समझ में आ गया phi solutions कैसे आ रहे हैं? It will be like e की power plus minus iota m phi, and if instead of writing plus minus, I have written m belongs to z. So function of phi would be a e की power iota m phi, with m belongs to z.
Yes, sir.
I think this is quite clear.
Yes, sir.
ठीक है जी. और अगर मैं ऐसा बोलूं कि this particular entire term I'm equating it to L into L plus 1, what will be, जल्दी जल्दी सोचते क्या होगा? देखो 1 upon p को उधर ले जाते हैं, 1 upon sin theta, it will be like d by d theta instead of writing del by del theta, because p is only a function of theta ना, तो इसको d by d theta लिख दो, खत्म करो. Sin theta into dp by d theta, and if I write L into L plus 1, take all these terms here, this will be plus L into L plus 1 minus of m square upon sine square theta, and I think there would be some p also. There would be some p also. Is that clear? Here we do a certain substitution. I'm just writing all these things for you. ये सब तुम बैठ के आराम से check कर लेना. We make a certain substitution, that is mu. We place it as cos theta, and then d mu comes out to be minus sine theta d theta. And when we do all these kind of substitution, I'm leaving it to you as a homework. You just find that this will come out as a solution. D by d mu, 1 by mu square, 1 minus mu square, del d by d ऐसा कुछ कर दिया, plus L into L plus 1 minus m square upon 1 minus of mu square. And this is fairly easy to see. I mean, this is something that I'm leaving to you as a homework. Don't worry. And for spherical polar coordinates, remember your theta must lie from 0 to pi. Is that clear? This structure of differential equation, if we'll do it, all these things in greater detail in like special functions. This particular differential equation, the solution of this particular differential equation are referred to as associated Legendre's polynomial. Associated Legendre's polynomial. अभी के लिए समझो इतना सा, इसलिए I deliberately choose to write P so that मेरे को बाद में दिक्कत आए. So the solutions are usually written as P Lm theta, or at times you'll find in book P Lm इस तरीके से. Are you getting my point? Well, this is something that you have to mug up. I have no other choice. Okay?
Yes, sir.
So you just use this kind of transformation. You'll find that I can reduce it to I can reduce this particular differential equation into this particular differential equation. If you have some mathematical physics book at your home, just find what are associated Legendre polynomial. You'll find those things in your special function, and just find what is the form of the differential equation. You'll find this sort of differential equation, and the solutions for this particular, the convergent solution. I'll write the convergent. Achha, there is another thing that I have to mention. I'll mention it. So the convergent solutions are referred to as associated Legendre polynomials, denoted by this. This is something that you're going to see in a hydrogen atom also. So I'm just giving you a sketch because this is a long thing to do right now. But overall, understand there will be some function of phi which is denoted by a e to power iota m phi. There will be some function in theta which are denoted by Legendre's polynomial PLM theta. Is that clear? And if you multiply it with the term phi, that entire term is called as spherical harmonics. I mean, quantum mechanics, if you remember, if I multiply it with e to power iota m phi, that entire term is called as your spherical harmonics. Achha, also
Yes,
there is a note I'm putting it here that only if L is only if L holds integral values, only then this will form convergent solution, otherwise not. So this is some mathematics, don't worry about it. You have to just remember only if L has some integral values, only then this particular differential equation will have some convergent solutions. Okay, this is something that you have to remember, otherwise it will be quite difficult. At times, we are concerned with azimuthal symmetry. We are concerned with azimuthal symmetry. Azimuthal symmetry means what? Azimuthal symmetry means that my function, my problem is such that the system is phi independent. Is phi independent, right? And if my function is phi independent, then it implies my m must be equal to what? 0. Because del square f upon del phi square then should be equal to 0. That implies that m must be 0. And if your m is 0, this particular differential equation then reduces to a form. I'll also say that these equations are self-adjoint differential equation problems. So all these things we are going to see in differential equation, but because I have to do all these things in first in electrostatics, so I have no other choice but to teach you. Okay, but because all the way if you are just doing total mathematics, then you will get bored. So this particular differential equation is called as your the solutions for this particular differential equation are simply called as your Legender's polynomial, not associated ones, but they are called as your Legender's polynomial, denoted by PL. You can say mu, and instead of mu you can write cos theta, because mu was equals to cos theta. Is that clear? Achha, what are the properties of Legender's polynomial that you should remember? Two properties that is significantly that we are going to use. One, the Legendre polynomial are orthogonal to each other. And what do I mean by Legender's polynomial? I'll write down some Legendre polynomials for you, and then we'll try to understand all these things in perspective to Laplace's equation in electrostatics. Okay, so Legendre polynomials, polynomials are orthogonal to each other. Orthogonal means what? Each other. Iska matlab, if I take my two functions are said to be orthogonal in the interval a and b. If I'm saying my function fm and my function fn are orthogonal in the interval a to b, it implies what? This particular integral should be equals to chronicle delta mn, or some constant into chronicle delta mn. It implies what? It will yield you either 1 or it will yield you 0. It will yield you 0 if m is not equal to n, and it will yield you 1 if m is equal to n. So two functions fm and fn are orthogonal if they satisfy such property. So similarly, Legendre polynomials are also orthogonal with some some constant here you will find. So in the limit from -1 to 1, orthogonal to each other in the range -1, 1, and I will write that my PLX and my PMX dx is written as 2 upon 2L plus 1 chronicle delta ml. This is something that you have to remember. All these things I'm going to do in your special functions, don't worry. But thoda sa itna pata kar lo. Itna you should be remembering. Is that clear? One of the properties that your Legender's polynomial must be orthogonal to each other. Is that clear?
Yes, sir.
And another thing that I'm going to do, I'm going to use some Legendre polynomial that I would expect from you to remember them, because otherwise every time a problem comes in your way, and then you'll not be able to figure out. So at least remember Legender's polynomial at least up to fourth order, at least to the fourth. Yeah, at least 3 तक के Legendre polynomial याद करो, मतलब n equals 3 तक के. So याद करने का तरीका क्या है? What is P naught x? P naught x is 1. What is P1x? P1x is simply x. What is P2x? P2x is 3x square minus 1 upon 2. And what is P3x? At least remember till this. और एक दिन तो पूछ रहे थे कि recurrence relation को कैसे solve करेंगे? At least remember at least 4 polynomials of Hermite, 4 polynomials of Legendre, और जो भी recurrence relation exam में है, just place these points there. Are you getting my point? And play with the option, because recurrence relation to derive them in exam is a very difficult. Okay, is that clear to you? And the last,
Yes, sir.
the radial equation that was left to us, that was d by dr, r square dr upon dr, and we equated it to L into L plus 1, and there was 1 upon R here, so here it will come as this. And if you remember, this particular differential equation is called as Cauchy-Euler differential equation. Cauchy-Euler differential equation. I did it somewhere, if you remember. अगर इसको तुम करोगे ना थोड़ा solve, तो you'll find that this is a Cauchy-Euler differential equation, and the solution to this particular differential equation will come out as R as a function of R. You will have some A R की power L plus B upon R की power of L plus. This is the solution that we'll get. So in the spherical symmetry, first thing that I taught you was that we solve the differential equation by the help of a method which is called as method of separation of variables. Now, in this, what we do, we multiply, we say that my potential is a product of three functions which are individually a single valued function of r, theta, and phi respectively. In order to find phi, I just equated it to some minus m square, and I found that the solution will be of the form a e ki power iota m phi. Then again, I equated it to L into L plus 1 theta. I found that the solution in theta would be some associated Legendre polynomials. And in particular, if the system has an azimuthal symmetry, that is, if the system is along xy and we look on xy plane from any angle, phi का मतलब क्या होता है? जैसे phi का मतलब क्या है? Let's say I am on the xy plane, and if I look at any direction, I'm having some sort of symmetry. मतलब charge is distributed in a manner. ऐसा समझ लेते हैं, charge is distributed in a manner that I can say that it is phi invariant. That is, if I see in this direction, if I see in this direction, there is no such asymmetry in the distribution of charge. ऐसा समझते हैं. So if I move along phi, I can see that it is a symmetrical case in whatsoever physical parameter it may be, but it is a symmetrical case. Then I would say that if the system possesses a azimuthal symmetry, that is, it is the function. That is, the problem is invariant of phi. That is, problem does not depend on phi, or problem is independent of phi. That implies your m must be 0. And if your m is 0, then this particular differential equation in theta reduces to this particular differential equation. And the solution for this particular differential equation are given by Legendre's polynomial, whose two of the most important properties are: one, you just list all these Legendre's polynomial, point number one. And also you must understand that these Legendre polynomials are orthogonal to each other. Further, when I was equating it to L into L plus 1, then this particular function, if I equate it to L into L plus 1, what I will get? I will simply get what? I will simply get a Cauchy-Euler differential equation whose solution will be of the form A R ki power L plus B upon R ki power L plus 1. Is that clear to you? Or is that not clear to you?
Yes, sir. Clear.
Okay, धन्यवाद. अब देखो, अब समझने की कोशिश करो, what are we up to? This is just a brief brief idea. Now for simplicity, initially we are doing Laplace's equation in spherical polar coordinates. In spherical polar coordinates with azimuthal symmetry. We'll do a few cases in non-azimuthal symmetry also, because there is a possibility in TFR for such questions to be asked, although they are difficult things to handle in examination, but I'll still do a few questions there. So Laplace's equation in spherical polar coordinates with azimuthal symmetry. That is, no phi dependence. So if we do not have any phi dependence, what does it imply? It implies that my solution B as a function will be a function of R and will also be a function of theta. Is that clear? Is that clear or not clear?
Yes, sir.
Okay. Okay. And the solution will be of the form R wala solution क्या था? A R की power L plus B upon R की power of I think L plus 1 ऐसा कुछ था, and then multiplied by PL cos theta. And understand these L will vary. So for each of these L, there will be solution. For each of these L, there will be solution. So what I can write that V r comma theta will vary from L equal to 0 to L equal to infinity, because L, for all possible L's, you will have solution. So what I'll do, what will be the total solution? Total solution will be the sum of all these solutions. That is A r ki power L upon B r ki power L plus 1 into PL cos theta. This is something that you have to remember any way out. Is that clear or is that not clear?
Clear, sir.
ठीक है, अब ये चीज थोड़ी समझने वाली बात है, बस आई हैव नो अदर ऑप्शन बट लाइक ऐसा ही करना पड़ेगा. ठीक है, अब ना समझ में मीटर नहीं समझ में आया तो एटलीस्ट रिमेंबर दिस रिजल्ट, इट नॉट एनीथिंग.
ये एक बार बता दो ना भैया प्लीज.
ओके, देखो what are we discussing right now? We are discussing Laplace's equation in spherical polar coordinates. If we want to like, this is a very long derivation. Like if you see in the books, it will go on and go on and go on and go on. So that I'm leaving it to you. You just do it on your own self. I'm just giving you an idea what do people do. So whenever we are talking of partial differential equation, the standard approach to solve such differential equation, one of the standard approach is method of separation of variables. When I'm saying method of separation of variables, what I do is I will simply write my V as a product of some functions. And these are functions individually of r, theta, and phi, respectively. Now, if I keep them together and if I move this particular thing there, what does it imply? On the left-hand side, you have some function of r and theta, and on the right-hand side, you have only function of phi. Or in other words, you can see on the right-hand side, I am keeping my r and theta as a constant. On the left-hand side, I'm keeping my phi as a constant. So overall, the consistency of equation says that if all these terms are being 0, it implies that if this is some constant minus n square, then this will be some constant plus n square. मतलब इनको individually आप constants equate कर देते हो, and this is the logic behind. So what we'll do, we'll equate it to m square minus n square, like, because here it was, I think, minus, but here, so I equated it to m square. If I equate it to m square, del square phi upon del square equals to is equals to क्या था ये? यहाँ पे क्या था? Is equals to, I think, minus n square phi, isn't it? यहाँ पे n square के बराबर लिखा था इसको. So minus n square phi, it implies del square phi upon del square f upon del phi square plus n square phi. You can write the solution in the form of e की power iota m phi. I mean, these are the solutions. ये एक solution हो गया. Then after having these solution, I have replaced this value here. Like I have replaced this value here, and I found that overall, here you have this on the right hand side, you have some function of r. On the left hand side, you have some function of r, and on the right hand side, you have completely function of theta. Again, apply again apply the that this particular thing can be equated to some constant, and this particular thing can be equated to some constant. I equated to something like L into L plus 1, which because this particular, if I write it in the format of L into L plus 1, eventually I'll find that because of this, there will be a format which gets created of Legendre's polynomial, Legendre's differential equations. If you search in your textbooks, dy dx 1 minus x square dy upon dx plus n into n plus 1 y, this differential equation is your Legendre's differential equation, whose convergent solutions are called as Legendre's polynomials. The convergent solutions to these differential equations are called as Legendre polynomials. Although there are some different polynomials also which are called as Legendre's polynomial of second kind, we are not interested physically because they represent divergent solutions. We are not interested there. Physically, physics-wise, we want only those solutions which are physically meaningful. The physically meaningful solutions to these differential equations are referred to as Legendre's polynomial. And the more general case, if I don't take azimuthal symmetry, then this particular general case would appear. These are called as your associated Legendre polynomials. So this differential equation when solved. This differential equation when solved gives you something called as associated Legendre's polynomial. Okay. Now, in particular, we have to also understand a few things that I have not done because we have not done special functions. So Legendre polynomials are orthogonal to each other, and secondly, remember these Legendre polynomials as I go along. Just remember them. धीरे-धीरे समझ में आ जाएगा what I'm up to. See, what I'm trying to do, I'm trying to write the solution Laplace's equation, solution of Laplace's equation in spherical polar coordinates with azimuthal symmetry. That is, I am not talking of some phi dependence. If I am not talking of some phi dependence, then my potential as a function of r and theta can be written as this. Is that clear? अब देखो इसमें थोड़ा समझने की कोशिश करो. Whenever let us say in electrostatics, because we are doing electrostatic right now, electrostatics, if we are asked potential inside a sphere, if we are asked potential inside the sphere, what term we should take? What do you think we should take? So the first term that you are seeing, first term into this PL cos theta, this will represent your potential inside the sphere. Because inside a sphere, you can have r equal to 0, and at r equal to 0, this will become singular. Is that clear? And if you are saying what will be potential outside the sphere, so this will represent your potential outside the sphere. Because outside, r may tend to infinity, and then this will become like infinitely large. Is that clear or not clear at all? ये चीज समझ में आई कि नहीं आई है?
Clear, sir.
हाँ भैया.
है ना? Is that clear?
हाँ.
I will develop a generalized approach also. Don't worry about it. But today, let us take a simple example and understand what I want to say. So, for example, I will take a generalized approach. Don't worry. For example, if a sphere of radius r, capital R has a potential phi naught cos square theta. आज टाइम कम है और चलो कोई बात नहीं, अब इसको कल करेंगे. पर एक समझने की कोशिश करो. If a sphere of radius capital R has a potential on the surface as phi naught cos square theta, what will be the potential outside? What will be the potential outside? So what we'll do, we know that potential outside is given by BL upon R की power L plus 1 summation PL cos theta, isn't it? Is that clear?
Yes.
Potential outside is given by this, and see, in any case, understand that potential function on the surface would be continuous. So just take at r equals to r. We know that at r equals to r, my potential is phi naught cos square theta. Is that clear? Potential at capital R would be phi naught cos square theta. Is that clear?
Yes, sir.
So what I would do, I would simply write that at r equals to r, my potential is phi naught cos square theta. Just replace instead of small r, capital R. Now, from the set of your legendless polynomial, just find कहाँ पर quadratic आने की संभावना है. So quadratic आने की संभावना कहाँ पर है? P2 तक. So don't go even till P3, because if you go till P3, there will be cubic, there will be x. You know that on the right hand side, you do not have cubic terms. You have simply quadratic terms. So if you start using because this here your L varies from 0 to infinite, isn't it? So start doing it. Place L equal to 1. So this will give you B naught upon R की power 1, P naught cos theta. Write B1 upon R square, P1 cos theta, and then you have this B2 upon R cube, and then you have P2 cos theta, and then this all is equals to phi naught cos square. Is that clear? I hope it is clear. And then
Yes, sir.
You just do one thing. You just try to find these values. You just try to find these B2, B1, and B0. You just try to find these B2, B0. So B0 upon R, and this will be 1. I think what is P1 cos theta? P1 cos theta is, I think P1 cos theta is cos theta. So there would be some linear term, and you can see on the right hand side, you not have linear term. And here you will have some 3 cos square theta minus 1. So this will be minus B2 upon R cube. And there will be some term 3 B2 cos square theta divided by 2R. So you just find the values of B1, B2, B0. Replace these value of B0, B1, B2, and you will be able to find the potential outside. You'll be able to find the potential outside. So potential outside, and just writing it here, we'll do it tomorrow, is given by phi naught upon 3 capital R upon small r plus 2 times capital R cube upon small r cube, and then you have this P2 cos theta. Is that clear? I think this you can do as a homework because there's lack of time. Overall, understand what I have done. I've just used the continuity condition of potential. This I'll explain you tomorrow. Don't worry. So your potential
V नॉट V1 V2 की वैल्यू निकाल के बस ऐड ही करना है ना उसको.
बस कुछ नहीं. V1